You get the scantron for Chapter-7, right? So we use those scantron for Chapter-1, 3, and 5, and 7. We'll start on the number 51. Right, so we'll start on Chapter-7. So just keep a study as usual. You study those lecture notes and read the book and do the CRE and do the online quiz. The online quiz is kind of like a homework. Right, so the next exam 2 on Chapter 5, 6, 7, 8 will be on November, I think on November 19th. November 19th, the second exam. So this week we will start on Chapter-7, then we will do the lab about gases. Gas we study in Chapter-5. I think it's a good review. So this week the lab is about the gases, like the gas law, Boyle's law, right? And the gas law constants that are when the P times V equals N times R times T. So like Thursday in the lab, and we are going to measure that R. Right. So let's start on Chapter-7. Chapter-7, in terms of chemistry, is getting deeper. Because in the first few chapters, we study how to calculate something, how to name something, and how to write chemical reaction equations. Right? So then we also know like some of those very common chemical behavior of some metals, like metal lost electron easily and become positive ions, and non-metal gain electron easily and become negative ions. Then we also learn, like in Chapter 1, Chapter 2, some metal lost 1 electron become stable, like sodium and lithium, and some metal or lost 2 electrons become stable, like magnesium and calcium. Right? So why that happens? And we study this chapter will give us some of those very fundamental understanding. The model or the theory we use try to understanding those kind of behavior of atoms or metals is the so-called quantum mechanics model. Quantum mechanics model of atoms, so this will be the title of this chapter. Right. So there are some stories, very interesting story about the beginning of this quantum mechanics model at the beginning of the 19th hundred. So at that time, a lot of scientists did some of those research and measure some of those behavior and measure some of those data, and a lot of those data they measure, a lot of those experimental results they measure, they get, cannot easily be understood in terms of those classical mechanics. What is classical mechanics? Classical mechanics is the so-called Newton's mechanics. You see that? Newtonian mechanics. So one like very important point in the classical mechanics is everything is deterministic, which means if you know the present condition of something, and you can predict him precisely everything in the future, if you know enough information, obviously. So then that kind of principles which come from the classical mechanics do not really apply to some of those experimental results they find out. For example, the behavior of electrons, behavior of some of those other smaller particles in the atoms, and later on more and more evidence, people even find like some of those behavior of atoms or even larger molecules, like some very large molecular biological molecules, their behavior cannot really understood purely use Newtonian mechanics. So those work was performed by many of those famous physicists, for example, Einstein and Bohr, Broglie, Planck, Heisenberg, Dirac, and Schrödinger. So they come up with some of those new concepts and new ideas. And then they put all those concepts together and put into a model. In that model, there is a very important equation coming from the last guy, and that pretty much summarize those important principles. So one important point in this new model is, compared with the old model, is for those smaller materials, smaller particles like electrons, maybe you can also apply same model to the proton and neutrons in the nucleus, is indeterministic, which means even though give you those information and you cannot predicting the future behavior of the electrons. So that is the beginning of this quantum mechanics model. Let's see some of those very strange behavior of some of those very small particles like electron. And we already know electron, atom, or molecular, even molecular is much bigger than electron, but still much smaller in terms of our daily viewpoint. For example, a single pack of dust has more electrons than the number of people who ever lived on the Earth, and that gives us some idea about how small those particles. But as we know, in chemistry, and most of the chemistry behavior is depend on the behavior of atoms, molecules, and then atoms and molecules chemical behavior depend on the electrons. So electrons behavior determines much of the chemical behavior of atoms. Electron behavior. So therefore, we try very hard to study the behavior of electron. Then we find out directly observe the electrons in the atom is very difficult. And for example, even you shine a light on the electron, and that will affect the electron, and that will change the electron's behavior. So we probably will gradually introduce little by little those concepts of quantum mechanics, so the strangeness, those awkward behavior or principle of quantum mechanics. But quantum mechanics is really so far a good model that it explains the manner in which electron exists and behavior in atom. And we accept that. We thought that is the best model so far because it can explain some of those phenomena we try to understand about material, use our usual daily life viewpoint, which means macroscopic viewpoint. And it helps us understand and predict, for example, the atoms that are the behavior of the atom are directly related to the behavior of the electrons. And we'll find some of those patterns, find out some of those behavior of the electrons. Then we use those behavior or pattern of the electrons to try to understand the behavior and pattern of the atoms. So as I said at the beginning, so why some elements are metal and others are non-metals? Knowing that is very important. You know, metal lost electron easy relative to the non-metals. They will become the cations. And then why some of those elements will gain one electron and some other atoms will gain two electrons before they become stable. And why some elements are very reactive, others are practically inert. We can also study some other periodic pattern in Chapter 8, Chapter 9. For example, the size of the atoms, which atom has a large radius, which atom has a small radius, they have some pattern. You go in, you compare with the periodic table, going from left to the right in the same row, or going up and down in the same column, and some of those very typical behaviors. So like that, we can also try to understand or explain those kind of patterns, use this new model. Right. So those experimental results or experimental data, most of them come from the study of the matter interacting with the so-called light, but in a broad sense of light. And light, when we see light, we usually think about the visible light. But in this chapter, when we say light, actually referring to all those electromagnetic radiation. And so that's like the one of those main, like those reason, we study this model, because at the beginning of that 1900, at that time, and many scientists, use light, shine on the material, see what are the reaction of those material. Also, some scientists try to observe light from the material, see what kind of light they observe from what kind of material. And so from those kind of observation experimental data, they say to understanding those data, the results, you cannot use like the Newtonian model to matching those data from your calculation, for example. Alright, so therefore we are going to, the first few sections in this chapter is about the nature of light. And as I said, the light is a much more broad sense. And now we know light has a wave nature, and that is like a common. Okay? So this is one nature, but we'll talk about some other nature of the light. So light is a form of electromagnetic radiation, and which means in the light you have two the sort of two fields, or two waves. So those two fields, they propagate and they travel in the form of waves, and two oscillating waves. One is electrical wave, and the other one is the magnetic wave. If you study like those basic physics, you know electricity and magnetism can interchange. Right. So in any of those light, visible light, UV light, infrared, X-ray, gamma ray, radio wave, and those electromagnetic radiation we use like in our cell phones, we all call them light, and they all have these two like waves. One is a magnetic wave, the other one is the electrical wave. And these two waves, they should have the same wavelength, the same frequency, and they travel in the same direction, but they oscillating in two perpendicular planes. So one oscillating in this picture is in this blue plane, and the other one is oscillating in the red plane. And these two planes is perpendicular. Right. So then you know like what is electrical field, what is magnetic field. For example, electrical field, it's just referring to like one region in the space. And if you have electrical field in that region, that means if you put an electrical charge in that region, that electrical charge will feel some attraction or some repulsion, or will see some force. And then we call that a region, that space is the so-called electrical field. And similarly, magnetic field is a region in space, So we'll talk about the region in space more in this chapter. So for a magnetic field, which means there are some part of this space, and if you put a magnet in that part, then magnet will feel some of those force. So then, one very important characteristic about this kind of wave or this kind of light, we call them electromagnetic radiation. They all travel at the same speed. If you put them in the same medium, for example, you put them through the air, you put them like in a vacuum. No matter what kind of light you have a visible light, they will travel with light of speed, the speed of light. If you have that infrared or the UV light, they will also travel with the speed of light. The speed of light is a constant number, but that will change a little bit depending on the medium. If you put those lights through like the air, they will travel a little slower than compared with the vacuum. If you put those lights through glass and through water, they also travel with different speed. But once you like have all those different types of light and you put them into the same medium or let them travel in the air, and they will travel at the same speed. And that is called the speed of light. And it is a constant speed. And in this chapter, so we will use C to represent this speed of light. So again, don't like confuse. You see, the speed of light is for the visible light. We're actually for all those electromagnetic radiation. So that means for gamma ray. For the X-ray, if you go to the doctor's office or you go to the dentist's office, you take those X-ray picture. So those X-ray, they also travel in this speed. And this speed, called as the speed of light, and it's a constant, but just relatively speaking, which means you change a little bit if you change from air to water. So then C has a number. Usually you use this number that will be precise enough in this chapter. And it is 3.00. Like you can use like 3 significant figures, and times 10 to the positive 8. So this is positive 8. Then unit obviously is a unit of speed, so it will be length over time. And in the SI unit is a meter over second. Alright, so this is one constant in this chapter, and you can use a lot. So like in the last chapters, we use also a lot of those common constants. We see we have 1 calorie equals 4.184 joules, and then in chapter 5 we also have a lot of those constants. We know that R equals 0.08206. I have this number. And so this number is very useful because that tells you how fast, how quick the something can travel. It pretty much is the limit and the limit of the speed in the universe. If you can produce something that travels faster than light, you will see those science fiction will come true, right? So you can travel like back into history and recapture what happens. So it's travel it's kind of like the speed limit. So then you can compare the speed with some other speed or some other waves. Okay? So the wave we talk about that has that 3 times 10 to the power 8 meter per second is the sort of the electromagnetic radiation, and that is travel the fastest material or fastest speed. Then compare with some other waves. There are some other waves, for example, the sound wave and the water wave, right? So those waves, they will travel at their own speed. Okay? The sound wave, for example, travels through the air, and that also depends on the conditions, depending on whether that air is a winter air, a summer air. But usually the speed of the sound is about 340 meters per second. It's much slower than the speed of light. So therefore, we have our like some of those live experience, and when we see those like a thunderstorm happens, we usually will see the lightning first, and then a few seconds, or maybe like not a few seconds, very quickly you will like hear the sound, depending on how far away that sounding is away from us. If it's far away from us, you have to wait for a little longer time. Alright, so that tells us we have some of those speed, and we have a different form of waves, but for that wave, we all have the same speed. Alright, so the characteristics of light, one is about a wave, and so that wave itself has those characteristics. Understand? So light sometimes behave as waves, which means to understand light, so those X-ray, gamma ray, we sometimes use this model, which means they behave as waves. But sometimes we have to use some other model, other concept. Now you have to see like what kind of characteristic the wave has. So we talk about a wave, we talk about, for example, the amplitude. So how high is a wave? Like when you go to you go to a shore or go to an ocean, go to the beach, and you see those wave of the water wave. It's a wave like a very large wave, huge wave, or small wave. So those we usually refer to the amplitude. Amplitude is the height of the wave. So usually when we see those kind of wave, we will see the middle line is kind of like those points. Those points here, we call them node. Call them node. So the amplitude is the height of the wave, which means you can measure from the node to some other points, and the highest point here, we call that crest. The lowest point here, we call that truth. Okay, so then the amplitude just pretty much measure from the nodes either to the crest or from the nodes to the truth. And that's sort of the amplitude. And what does the amplitude tell you? The amplitude tell you whether you have, that's pretty much a scientific term is intensity. Okay? And then that pretty much, if you can see that, will tell you the brighter or dim. And obviously some of those light cannot see them, but so therefore you can see that pretty much about the intensity. How intense? Is it very intense? It's kind of easy. Right. So another characteristic about a wave is wavelength. I use that word. So wavelength misspelled. L-E-N-G-T-H is one word. That's wavelength. Is the measure of the distance covered by the wave. So now what do you mean by the cover? This looks like from what to what. What you measure is you measure, for example, from one crest to the next crest, and that's called wavelength. Or you can measure from one tooth here, and the next one with somewhere here. That's what the same wavelength. Or you can measure alternatively the node. So measure from here to here is one wavelength. If you measure from here to right away the next node, that will be the half of a wavelength. Right. And so this picture will give you like even clear idea. So here is a node. So again, this is a node, and also this one, and this one, and this one. So these are called nodes. And the higher point, we call that crest. Lower point is the trough. Right. So another very important characteristic is frequency. I have the frequency. So frequency is the number of waves that pass a point in a given period of time. So or you can think about how much like circles, because wave can produce from like one circular motion. So each wave is equivalent to one circular motion. So how many circles that the wave like goes through in like some given period of time? Usually that period of time is per second. So that will be the common unit that called that circles per second. And circle, usually we don't think in that as a unit, so therefore we just think about per second. Okay? You know this second to the negative 1. In math, that means 1 over second. 1 over second. So this 1 over second has a common name. Okay? We call that a hertz. So you know, like when you buy, for example, a computer, you want to see, for example, the speed of the CPU. Now the computer, the personal computer, the so-called personal computer PC, is very powerful. So they have like a quadruple core or dual core is kind of become like out of date, right? So that means they have 4 processors, and each processor like some like maybe 3.00 gigahertz. So those hertz referring to those hertz, and then those gigahertz obviously those common prefix. So giga means 10 to the positive 9, and right. So you can use those prefix to any of those units. Right. And so then you also want to know like what is the energy that some of those wave carries. The total energy of a wave that carry that has depend on couple of things. Depend on the amplitude, depend on the frequency, and later on we'll see the frequency is related to the wavelength. Okay? So for now we'll see that the total energy is proportional to this. And there's some other variable we think about, but usually they're not that important. Obviously, how much total energy you get from those light depends on how long you shine the light on. If you shine the light just briefly turn on and off, and you only get a burst of light. If you shine the light on there like 24 hours, you get more energy. So for those conditions given, the energy of the light depend on these two, depend on the amplitude, which means the height of the wave, and it also depend on the frequency. And, so then we have this few like very important quantity, amplitude, wavelength, frequency, energy, and then we'll see what are their interrelations, what are their connections. So one common connection we want to study is about the connection between, or the relationship between, for example, the wavelength and the frequency. Right. So then, we'll find out, for those light waves, the visible light or the X-ray, gamma ray. We said they all travel at the same speed. Okay? And when you will see they travel all at the same speed, so then depending on the wavelength and this wavelength frequency will have those relations. Okay? So if you have a longer wavelength, and you will have lower frequency. I don't know, I don't remember the word I use in the lecture notes, but just any word, just make sure they were matching out like this. So what you find out is the wavelength and frequency are inversely proportional. So this is this one is longer wavelength, and this one is lower frequency. Understand? If you change the words, so then you will see these two like inversely proportional, and so longer, let's say compare with shorter, and then the frequency will say either lower or higher, right? But these things you can see, you measure something either longer or shorter. The frequency, that means how quickly they vibrate, either lower or higher. Right. So these two pair of words that were matching, and from this matching relation, you will see they are, you find this. So this means that the wavelength, the frequency of those electromagnetic waves, so you call them light, in a more general term, is inversely proportional. So I don't have to use the word again. So this inversely proportional. So that can be given by this equation. And this equation, I think the book gives you in two formats, but that's the same equation. So I usually prefer with this equation. So remember, like we said, all those, they have the same speed. The same speed, we call that C. And C has that number, so this C has a number 3.00 times 10 to the 48 meter per second. Right. And from this equation, you will figure out the inversely proportional between these two letters. And this first letter called lambda, representing the wavelength. The second letter is the Greek letter nu, representing frequency. So therefore, wavelength and frequency, wavelength and frequency are inversely proportional. Right? So that's similar as that Boyle's law. So as I said, you probably want to review those other chapters, prepare for the exam too. Right? What Boyle's law tell you? Boyle's law tell you pressure times volume equals constant. Right? C is a constant. Right? So therefore, you can see they have the similar proportionalities. Okay? So lambda times nu is constant, okay? And pressure times volume is constant. Now we know like pressure and volume is inversely proportional. So you increase the pressure, and your volume decreases. And that's similar here. So you increase the frequency, then your wavelength is getting like smaller. Right? I think that is one equation. You can do it simple, so you're going to use that many times in this chapter. So know that equation. And for I will write this equation, so that the equation you just learned in this chapter, so that C equals lambda times nu. And so maybe make a note here. So the C is constant and equals common number is this much meter over second. And then this lambda is our wavelength, and then this nu will be our frequency. Okay? So if you use this unit for your speed of light, and your wavelength should have this meter, and your frequency should be 1 over second. 1 over second, also called hertz. And this not mean mass, this meter. So this is meter. So this meter M is meter. So I think those are easy questions. Just remember like what you did in the previous chapter. You have to know how to convert those different units. If you want to use this equation to do the calculation, right? So make sure so your speed of light is that amount of meter per second, and that means your wavelength will be meter, and your frequency should be 1 over second. If I give you the wavelength not in meters, you have to convert that into meters. Right? If I give you the frequency not hertz, you have to convert that into hertz. Right? So here's one example. Right? And you want to calculate the wavelength. So you want to calculate the wavelength in nanometers of a red light emitted by a barcode scanner that has a frequency of this. So very easy calculation. And so you are given the frequency, you want to find a wavelength. Use this equation I just write on the board. So you use C equals lambda times nu. And this number is our nu, our frequency. So I said, if you want to use this number for the speed of light, and your frequency should be in 1 over second, so that's good. We have 1 over second. Okay? And so then let's first use this equation and solving for that lambda, because we don't know lambda. But if you use 1 over second for frequency, you use that speed of light for the C, what you get is a meter. But that's okay. So once you get a meter, you can convert that into nanometers, right? right? So you can solve this equation like this. You just solve altitude 3.00 times 10 to the positive 8 meter over second. So I just do a simply substitution. So I have this C, and I know this number for C. And then I will write on the other side. So I don't know what is the lambda, so I just keep writing what is the lambda here. And then so we have this frequency, which is 4.62 times 10 to the 14 1 over second. Okay? So in this example, it's relatively easy because those frequency given to you is in the right units, just hertz, not in megahertz, not in gigahertz. So therefore, you simply put this number in, and then you can see, right? So then you can see the unit. So you can count them out right now, but if you prefer count out them later, you want to find this number. So what you do, you will divide by 4.62 times 10 to the 14 1 over s. You do here on the right side, you do the same on the left side, 4.62 times 10 to the 14 1 over second. Right? And now what happened is this comes out with this. Everything comes out, okay? Which means the number comes out. Also the unit comes out. 1 over second comes out with 1 over second, and the same number. And on the left side, okay, so you have this 1 over second here, and then here, even though I cannot circle 1 over second, just have the second as the denominator. So these two will simply cancel out. Right? So you get this lambda on this side by itself. Another problem is in your calculator, just make sure how to use the calculator. And so I will rewrite 3.00 times 10 to the 8. Now the unit only left over is a meter. And what I want to rewrite, because I want to emphasize the way of use the calculator, do the calculation correctly, is by put these two numbers in the parentheses. Okay? So in your calculator, turn your calculator on, and you can enter those numbers as what I write. Okay? So you write 3 times 10 to the positive 8. Okay? Then you will say divide. Okay? And so divide comes from this line. Okay? Now what next is enter this parentheses. Okay? So press parentheses. Okay? And then press 4.62. Okay? Then you will see time 10 to the 14. Okay? And also depend on your calculator, so make sure you see where is your cursor. Okay? Right? And so now once your cursor onto the baseline, then you close the parentheses. Okay? Right? So what I get now, right now, is like this number in my calculator, depending on your mode of the calculator. So I get 0.000, another 3 zeros, and 649. What's the unit? What are our unit now? Only meters. Right? Only meters. And now let's talk about how you convert into the unit that you want, right? So in this problem, you want to convert into what unit? Nanometers. Okay. One easy way I talk about in things like Chapter-1 to memorize those relations between those meter, nanometer, and hertz, megahertz, gigahertz. Okay. You're doing something like this. Okay. So you know you have this, you starting from like whatever that unit has a prefix. So you write 1 nanometer, okay? And so then you find out that nanometer equals how many meters, okay? Because right now you have the meters, Understand? Alright, so then you memorize those prefix has a numerical value. Right? Daisy means 10 to the negative 1. Sunny means 10 to the negative 2. Milli means 10 to the negative 3. Understand? Right? So this guy is nano. Nano means 10 to the negative 9. So what you do is very easy. So you see this n here, just replace this n by 10 to the negative 9. So therefore you have 10 to the negative 9. And you already replaced the n by 10 to the negative 9. So therefore what left over is a meter. Right? So you get those kind of equations very quick. Right? And right. So you get that, that's good. So now what you do, you are going to use this equation. You understand how I get this? So I get this equation very quick by replace whatever that n is representing for. Okay? So if I want to change into, for another example, dm, that dm is decimeters. So decimeter, what is the relation between decimeter and meters? And decimeter, as we said before, so this is deci. Deci means 10 to the negative 1. So just replace the d by 10 to the negative 1. And what left over is meter. Right? And you get this equation very quick. Alright, if you have that 1 m, which means millimeter, and so this is milli. So that milli means 10 to the negative 3, right? And you just replace 10 to the negative 3, milli by 10 to the negative 3, and then you still have this m, so therefore you find out those. Even though those sometimes look strange, but you can multiply 1,000 here, multiply 1,000 there, then what you get is 1 meter equals 10 to the positive 3 mm. So those come from some other way. Alright, so now let's use this equation to the conversions. So you have this the wavelength is how much meters, but the question asks you in nanometers. Understand? So it will be our old friend. What is our old friend? I told that many times. What is our old friend? Who is our old friend in this class? Who is our old friend in this class? Conversion factors. Right, so I have this one. Now this one, just as like a practice. So I have this number here written in like decimal numbers. Now you can convert this into like scientific notations. 1, 2, 3, 4, 5, 6, 7. So I will stop here. So I can write 6.49 times, how many times did I move to the right? 7 times, so therefore will be negative 7. Right? And right now it has this meter. Right? So our purpose to use the conversion fractions is to cancel out the meters, get what you want. What you want is nanometers. Right? So you can pick out this equation. Understand? Now this equation, as written now, has 10 to the negative 9 together with the meter. Right? So you will just put a 10 to the negative 9 here, and you put the meter here. Right? Then you put 1 nanometer on top. Right? So once you have the fraction right, You see, you can still check it, see if you get it right. Okay? You probably think that's right, but you did not get it right. So you cancel that out, then that is right. Okay? Right. So then you can use calculator, or you can use those order words. Right? So you have 10 to the negative 7 here, you have 10 to the positive 9 here, and we call them, we have the same base. Right? And so what you will do is you have 10 to the negative 7 divided by 10 to the negative 9. That equals 10 to the negative 7 minus negative 9, because you when you divide, you're subtracting the exponent. Okay? So what you get is 10 to the positive 2. Right? So sometimes you don't even have to use a calculator. Okay? So you get 6.49 times 10 to the positive 2. And then obviously this has the unit in nanometers, and this will become 649 because that's this number not too big, not too small, so you don't have to use scientific notation. I think I do through like this little slower because this pretty much the kind of confusing part in this chapter. So I think the equation is not too much. Just know like how to convert those units. Right. So that's the result from this example. Right. So you put on which for 51, right? 71. You put on the 7. You have that sample, right? So some of those CRE for some of those previous chapters, chapter 4 and chapter 6, I have not put on the internet yet. So if you worry about like some of those like your grade, you can just ask me. So I mean not like for one chapter. So I think quite a few chapters I don't have time to. Alright, so this is about very similar using this equation I write on the board. Right? So what you want to calculate is frequency. So what do you get? What do you get? E. Okay. I don't remember how you get E. I get E. Sure. You divide?
Yeah.
Okay, you want to write your calculation here?
No.
Yeah, write it. Let me see if you need to write or not.
You can look here. Oh, I got it. Sorry.
Okay. Where else get it right? Where else get E? I will finish your calculation. What do you get?
Okay.
So write here. Or erase this here. And so use this part, and we can see that. Maybe you can use those.
I always do I do the conversions before I plug it into the problem. So the first thing I do is figure out Newton meters, right? Nanometers
Nanometers?
to meters.
Okay, so you take the C divided by the wavelength. 那个数字的 wavelength， I think you probably like the what before you do this.
So that's what, when I do this,
Uh-huh.
that's what I take care of.
Okay.
How do you know how many, decimal you have to move?
You just move until you get a number that is smaller than 10 and larger than 1. So you, right now you have this number, you move to the right.
How many, yeah.
You move until you get a number that no zeros, so let's say you will get a number.
Then
You
start
don't want to get like, you don't stop there, you get 105. 105 is smaller than 1. You don't want to get to out of 7, you get out of 7 then more than 10, 50%.
Okay.
Yeah.
So a number that less than,
Less than 10, larger than 1. Alright, good. I think that's, if you want to keep the right number of single figures, you will write like 5.22, right? Okay, any questions? Okay, I mean, Maggie, you can explain what you did.
So the top part I converted I wrote the wrong thing there, but the nanometers to meters first, and then I plugged that into the formula frequency equals speed of light over wavelength. We know that speed of light is constant speed, 3.00 times 10 to the 8th, and then over the meters that we converted above there, and then the meters cancel out, and leave us with 5.22 times 10 to the 14th.
So there are some of those details, like some people are asking when you have those numbers in your calculator. So this part from your calculator, you get 0.000000052 as 522 something.
Yeah.
And this will be the meters, right? I mean another thing. So here, so this I got confused here. So I mean this number here. So you put in the calculator, you get something like this, right? And how you convert this number? So I think what this asking how you convert this number into that? You by just using those sign implementations. All right. Any questions? So do another practice. So we have this. You want to find out wavelength. So this practice is very similar as the example, right? So you want to find out the wavelength in nanometers. I think this one I remember the answer. What did you get?
B.
B. Yeah. Very good. Yeah. Okay, so what do you do? What equation you use for those kind of problems? If you are given either the wavelength you want to find the frequency, or frequency you want to find the wavelength, what equation you use? That's the equation we talk about today. Only one equation, right? What equation should we use to find those problems? In that equation, the C equals lambda times 0. Right? Well, this equation, C is 3 times 10 to the positive 8 meters per second. What do you find out? Still working on that? How do you find that? Yeah, for this one, you pretty much plug in the values because this is the first, is 1 second, right?
Right.
After you plug in the value, what unit you get for the wavelength? You get meters, then you just do one conversion, right? Very good. Very good. Yeah, that's the answer. Okay, want to write out? Just erase what Megan write, just try to write the code to the screen.
Yeah.
Okay. Need help?
No, I think I got it. It's got it.
You get it right?
Yeah.
Where's your, that's a good idea, to print out the lecture notes and do the practice, right? Are you okay? the calculator before we put them in the parentheses, right? And then also pay attention to what comes out. You have a cross means 1/2. Yeah. So that S comes out. Alright. Now you get it? Well, you did it this time, probably that's a problem because you don't have that nanometer meter convert right away, right?
Yes.
Yeah, so you get that number like in meters, but you won't convert it in nanometers. What you do, what you did, how you convert that meter into nanometers? You do what?
Oh, yeah, just.
Oh, yeah, yeah.
Yeah, just convert it.
So you either like multiply by 10 to the positive 9 or divide by 10 to the negative 9. Any questions? Yeah, question?
Okay, so I divided this one by.
Yeah, usually that's the problem. When you divide by sometimes this, you put this number in your calculator in the parentheses.
Yeah, I put it, oh, what one is parentheses?
That one is okay. Okay, good. What you get is okay. So now, you see, values unit, what you get here, so the meter, the top is meter per second, and here is 1 per second. So second come out. Good. So I know you have meter, right? Now do a conversion. Right? So conversion like what I used before, like 1 nanometer. You can write somewhere 1 nanometer.
So it's 1 nanometer is,
10 to the negative 9 meter.
okay,
So now you think about how you have that equation, right?
yeah,
Do a conversion.
yeah, okay.
See that before?
Yeah, I got it, thank you.
I got it.
So just a minute. Okay, now keep going. So you have that, okay? That's still alive. And the 4.2 I can do the whole it's the this one. 8. There's a minus 3 there.
No, there's not.
I think there's a space between the 10 and negative 8. How do you can begin the space? Or linearly? Go back now, try to use lead. It is I think that's 8 or the negative is not really negative. Let's just starting here. Clear all those. Clear all the values, see, right? I see that parentheses 3 times 10 to the.
Oh, that one.
That is only for the square, right? You have 2 of them. That's clear. And negatively. Then you move the cursor, right? Don't change anything, and move the cursor and right this time. Then close the parentheses. Depends on how you set out the calculators.
It's full of market.
So then change to the positive A. Now you have to use this arrow to move the cursor that we're talking about. Yeah, I think that's why you're wrong. I think that is that is not negative, positive. It's just read those.
I did what I could. Thanks, John. Yeah? Yeah, it's tear in your eye right now. You crying? It's crying over my slots.
Another problem is. No, that's not my answer. So you will write those on your worksheet. So So that's 10 to the body 8. That's fundamental. 10 to the body 8. So now we have 10 to the negative 11, right? Write those all the units. So that's, I think you that's pure parity, like what we did before, right? So you have here you have meter over a second. Right? Yeah. So this is meter over a second. And here is just we repeat it 1 over a second. So you don't have to write it. So whenever we see first, it'll be 1 over a second.
I was like 20
So
something one, which is a lot less than the.
I don't have a meter.
Oh, yeah.
So you have a meter, right? So look, our working.
The like relationship,
Already nanometers. So you want to see 1 nanometer?
Is that free?
Yeah.
1 meter. You can write it with 1 meter. Now on top of it, we have 49 actually.
I use it for my calculation.
At the bottom is 1 meter. So now you can just have a cell work. Either out, and positive 9, negative 11 become negative 2. Okay, any questions? I like to see that. So any questions, just make sure you practice. And right, Brad? So you can find what it is.
I just wrote out the equation and plugged in the values variables.
What equation you use, Jack? What equation you use? This equation, right? And what is this C? Let me show you how the unit, right?
So you already know the constant for your light, and you just plug in the frequency that they give you.
The frequency, you cannot simply plug in. The frequency given to you is what here?
It's in hertz.
Hertz. What do we mean by hertz?
1 over second.
1 over a second.
Right.
When you have 1 over a second, you have the same unit.
Right.
So therefore, he replaced that simply by 1 over a second.
Yeah, and the seconds cancel out, so you're just left with meters.
Mm-hmm.
But they want the answer in nanometers,
Right.
so you can use either of those two conversion fractions.
Yeah, very good, Bruce. Thank you. So this either you write that 1 nanometer is 10 to the negative 9 meters. Okay, here, everyone see that? Or you can write the other way. Okay. 1 meter 10 to the positive 9 nanometers. Very good, very good. Okay. And that's why you get pretty good on the first exam, right? You get 30 out of 30. I mean, putting on the spot, but all right. So that's, I think we have this few questions in the slow. That means those are the typical confusion point of the chapter and the units. So it's kind of review what you learned in the first few chapters. All right. So obviously here, so I already told you in the program, so everything should be in nanometers. So therefore, everything here, assuming should be nm and nm and nm and nm. And I think if I did not write that, so therefore some of you probably forget in the question. And you try to see that if you get that answer, right? And that's wrong. All right, so that is the first cover of the CRE. So then we are going to talk about some other characteristic of those light. And one characteristic is about the colors. And the color of a light depends on this either one of these, because these two you already see from the last two CRE, you can interconvert. So sometimes you will see the color depend on the wavelength, sometimes you will see the color depend on the frequency, so either one is right. And usually the visible light has the rainbow spectrum, has the red, orange, yellow, green, and blue and violet. Right. So then, for an object to appear to have some of those visible light color, it means it absorbs some of those frequency or the wavelengths and reflecting the other. Right? So this picture tell you this clothes that appears as red because it absorbs all the other wavelengths or frequency of other colors except the red colors. So reflecting that frequency that all the wavelengths that is for the red, so therefore this clothes appears as red. All right, and so that's about one connections. Another connection is the amplitudes, as we talked about before, is about brightness and dimness. And so again, that color and wavelength is pretty much matching these three examples of colors for the visible light. And we see this in the background, so this is red. Okay? And red has a longer wavelength, so therefore we have this wave has a longer wavelength. Okay? And then gradually go from red to the violet and go through those yellow, orange, and green and blue, and the wavelengths getting smaller and smaller. If the wavelengths getting smaller, then the frequency getting higher. Frequency means how much like those wave goes through like one point at a given time, and so therefore you have this matching pretty much. So a longer wavelength, okay, and a little shorter wavelength, and even like a shorter wavelength. Okay. And this picture did not show you in reality, just tell you dim or bright. Probably we shall make a picture for this wave, that means these two waves have the same wavelength and frequency. And by comparing this wave on top, a little like smaller, it means the amplitude is smaller. It's kind of very gentle waves. You think about those ocean or the sea has those water waves, kind of very calm. And then this wave, the amplitude very high, then you kind of like very high sea. And so then those highs will tell you whether it's bright or this is a very bright picture, and then very not a bright picture. Okay, so we are going to see like some other characteristic of light, right? And wave characteristic was first discovered. It was easy to discover. I think about 200 years ago, there's a scientist called some Young, Y-O-U-N-G, Young. The very famous Young's like a scattering experiment. So what he did is, take a beam of light, then in the path of the light, he put like two small narrow opening. Then behind that, and he found some of those bright and darker patterns. So what kind of characteristic that produce those kind of interference patterns? That is the wave characteristic. So then this characteristic, called that particle characteristic, was named by Einstein. So even though before Einstein, some other scientists get some of those ideas about some of those radiations. So for example, Planck studied those hard object radiations, and so they find out you have to have those kind of idea, which means the energy from those radiation is not continuous. And so therefore, this idea is very similar as this this Einstein's particle idea. Okay? So Einstein proposed that energy of light is quantized. What that means is if you have a light, you cannot have any possible number for the energy. And the smallest package for the energy depends on the frequency or the wavelength. And that will be the smallest package. Then your total energy for your light depends on how many of that small package you have. If you have one small package, you will have that amount of energy. If you have two small packages, you will have twice of that energy. If you have three, have three times. Right? So Einstein calls that is one quantum or one photon. Right? And he also proposed one equation. That equation under this guy because he found out that quantum this kind of concept, right? So you can calculate how much energy one of that small package that has. That will depend on the frequency of that light. And that is more and more dramatic if you talk about the light that comes from, for example, laser. So laser has only one frequency or one wavelength. Okay? Therefore, you can calculate precisely what is the energy of one that small package in one beam of laser. Right? So therefore, this will be our second equation. So the first equation here, and the second equation will be E equals H times mu, and H will be another constant. Okay? So C is a constant, H is a constant, and this H is sort of the Planck constant. So H equals 6.626, and joule times second, and it is a constant again. You don't see this in this few chapters, you can use that a lot. Right, so therefore, if I give you frequency, okay, you can use this right away. Frequency usually will give you, okay, so this nu will usually give you 1 over second, which is the first. Okay. If you take this unit and multiply on this unit, so this unit has a joule over second, so the second on the top, cancel out the second at the bottom, you get the joule, which is the unit for energy. Right? If I don't give you the frequency, if I give you wavelength, and from the last cover CRE, you know how to convert. If I give you wavelength, you can find out the frequency. Okay? And once you have the frequency, make sure the frequency should be in 1 over second, and again you multiply, and you will get the energy for one photon. Okay? So this is the energy. So this, let me make a note for one photon. If you want to convert, you can convert. If you don't want to convert, you can use this equation. This equation pretty much just combine what you do. Okay? So you know, like when you count, if I give you lambda, which is the wavelength, you want to get nu. Okay? You want to get nu, and you will get. So you will get nu equals c divided by lambda. Everybody agree? Right? If I give you lambda and you want to use that one, then you do a convert, use that, right? So once you have that nu equals that, and you replace that nu by h, by nu by that, so you have h times c divided by lambda. Understand how you get this one from this and that together? right? All right, so either one, but again, unit is the problem, okay? If you want to use the first one, what unit should you use for the frequency? 1/2 is also called what? Hertz. Okay? If you want to use the second one, then you list all those. I write them. If you want to use again, you want to use the first one. Your units for the new, which means the frequency, should be what unit? If you want to use the first one, what unit should you use for new? Hertz. Hertz means 1/2, right? If you want to use this one, why you want to use this one and that one depends on what it gives you. If you have the new, use this one easier, right? If you have the lambda, use this one easier, right? Now if you want to use this one, and you already know what number should you use for h. H should be what number? Look at this number, right? And so this number has a unit joule times what? Second. Okay, so once you have this number, you can change this number, but usually you don't change those numbers. Okay? So keep this number. If you keep this number, and you also know what is your common number, common unit for C. So C should be what number? So C should be 3 times 10 to the positive 8, right? Positive 8. And what is the unit? Meter per second. Meter per second, right? Now everything work to come together, right? So if I use this unit for C, use this unit for H, now what unit should we use for lambda? What unit should we use for lambda? Should we use nanometer or meter? 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 Right? Now see why is a meter, right? And let's all just keep the unit. Just keep the unit. So for this equation, the unit for H is joule times what? Times second. So let's put this one here. Times second. Right? So this is H. We are only going to work on the unit. You already know what unit you get if you use this number for C. The unit for C is a meter over what? Okay, so now this is H. H times C. Okay? C will be meter over second. Now H times C, this equation tells you H times C then divided by what? This equation tells you H times C divided by what? Divided by lambda. Right? Divided by lambda, therefore we have to divide by lambda, and then let's figure out what unit should we use for lambda. Okay, let's see if we use meter. If I use meter here, let's see what comes out. So second comes out, what else comes out? You can see that makes sense, right? It's totally makes sense. Okay? The meter comes out, what left over is what? Joule. And what do you want to calculate? The E, right? The energy. And energy has joule that makes sense. All right, I think that's probably enough. So let's do a calculation, and you want to calculate the energy of one photon. Okay, so be careful for one photon. Remember that formula for one photon. Okay? Of yellow light with a wavelength of 589 nanometer. Okay? So give you wavelength, and we have two equations. So we call that E. To each side for one photon, I will put a subscript here. Okay? I will just call that E subscript photon, which means for one photon. So one photon, one equation is H times nu. So the other equation is E photon equals Hc divided by lambda. Okay, now for this particular problem, what equation shall we use? Shall we use the first one or the second one? I mean, you can use either one, but leave it easier straightforward. What I'm going to use if I give you the wavelength? use the second one, okay, let's give this one, right? Now remember what we said, use this second one, so therefore let's just write this, 3.626. This number cannot change because that is, I mean, relatively don't want to change that, that's constant, right? I just write that, right? So what number should we use for C? 3 times 10 to the positive 8 meter over second. That's very, very good. So don't waste your time. That's do the practice every day. So now you have that. Now what should we do for the lambda? What unit should we use for lambda? Meters. Now what give to you for this lambda? Nanometers. Okay. Now you can either do the conversion in the formula, right? Or do the conversion like as one extra step. Right? Well, let me do like as one extra step first. Okay? So I write 589 nanometers. Okay? Right. So obviously you want to count out these nanometers. You want to get the meters. Right? Right. So what do you use? I can write 1 meter. If I write 1 meter here, now what? 10 to the what? 10 to the positive 9, right? Right. But I think initially I show you the other way, right? But you can from the initial what I initially show you like this. I said 1 nanometer equals 10 to the negative 9 meters. Right? So you can either use that one or use this one. I think that's why we get people confused. Right. So what you get is 5.89 times 10 to the negative 7 meters. Right. I omitted some of those details. Right. All right. So any questions? Do you know how I get this 5.89 times 10 to the positive 7, 10 to the negative 7 meters? You know how I get this number? Right? Here is the positive 9. Right? So 1 divided by 10 to the positive 9, which means this 10 to the positive 9 on the top become negative 9. Right? And negative 9. And so that's 589, which means 5.89 times 10 to the positive 2. So positive 2, negative 9 become negative 7. Right, so you will put that number in here. So in that 589 times 10 to the negative 7 meters. Any questions so far?
I think it's supposed to be negative 8.
-8? Which one?
With meters.
No, -8. Let's see, maybe you're right, let's see. So this one here, right? So this one become, so I write in this number 589 times 10 to the positive 2. Do you agree? Right? 500, that means you will have a 10 to the positive 2. Right? Right? Now, I will say multiply by 10 to the negative 9. Where does the 10 to the negative 9 come from? From this positive 9. Right? So this positive 9 is in the denominator. You flip that over on the top, that becomes negative 9. That's kind of very simple, those algebra. Right? So you have those exponents, and the denominator is positive, and you flip that over on that, it becomes negative, vice versa.
Okay.
Yeah. Right, so that's all that problem. Right. Now let's see the unit count out. Now before we go on to count the unit, any other questions? No question? Right. So what kind of out? You see what kind of out? Meter cancel out. Alright, so meter here, cancel out that. Say second, do that way, second and second. Yeah, see that? So what is the unit left over? The only unit left over is this joule. Alright, so do a calculation, and if you want to simplify, you can simplify, otherwise just use your calculators. Right? Use your calculator, those numbers on the top is okay. You don't have to use parentheses. Right? For this number at the denominator, so make sure you put that in the parentheses. Okay? Those numbers on the top doesn't matter. Just use your calculator one by one. Okay? And so what do we get? I think I get 3.37 to keep like only 3 single figures, right? Negative 19 and joule. Am I right? Right. I think that's it. 3.37 times to negative 19 joules. Right? So make sure practice, right? And practice in the class. So when I do it, you can do it with me. Right? And before the class, and that's why I don't like write anything or don't remember something. I just do that in the class. Because when I do it, I hope that means give you some time, and you also do that. Right? So what did it say? There's a 3 process about learning. Right? So what you hear, you forget. What you see, depends on your study style. Okay? So what you hear, you forget easily. But some person is kind of listening person. Okay? And what you see, you remember. Okay? And then what you do, you just really you really understand. Okay? Right? So listening and read and also do it. I think do it is the most. So those 5 senses is the most sensible activity. So now those days you have more and more technology, just everything like internet, iPad, and you still want to use those old technique like paper and pencils and write and practice. Right. So this is another example. In the last example, we said what we did is calculate the energy of 1 photon. Okay? 1 photon. So we can do the same for this program. Right? So 1 photon depends on the frequency and the wavelength of the light. Right? For this program, that give you like a pulse. In that pulse, you can think about it has X, X number of photon in it. You understand what I'm trying to tell you? Right? So you have a pulse of lasers. That means you play those laser tag, you switch on your laser gun, and so you produce a pulse. In that pulse of laser, you know you have a frequency or wavelength for that, right? Well, that's laser, so you only have 1 frequency or 1 wavelength. And in this laser, the wavelength is given 337 nanometers. Right? So then you don't know how much photon you have in that pulse. So for every one photon, later on in the other sections you learn, it's coming from like one of those activities. Right? For example, it can come from like one of those transition of electrons. Right? And some of those radiation, some of those lights, like those gamma ray, X-ray, they are not coming from electrons, they come from some of those activities in the nucleus. But anyhow, so for each one photon, in the last example, we know how to calculate what is the energy for one photon. So then if you want to think about what produces one photon, you call that one activity. So maybe one decay of a nuclear, or maybe one of those jumping up and down of the electron. So electron has energy. If the electron in a high energy state fall back to a lower energy state, it will create a photon. Now in that beam of pulse of laser, and it has X number of photons in it. We don't know what is that number. The question for this problem is ask you what is that X. Right? So if you take X and you times that number, we call that E photon, which is the energy of one photon, and that will give you the E of the pulse. So that is the idea, right? So you have that pulse, and it has X number of photons in it. Because it's a laser, so all the photons has the same frequency or the same wavelength. So therefore, all the photons has the same energy. If you have X number of photons, so X times E photon will give you the total energy in that pulse. That makes sense? Very good. So then, so this equation comes from like kind of like our common sense. We don't have that equation really. Someone like just carry that equation, right? Right. So X is the one you want to find out. So therefore, you have to say, do we have some other numbers? You want to find out X, you have to know this number, and you have to know this number. Do we know this number? Do we know the energy of that pulse? Right? Right. That is given. This much mj. What is mj? Millijoules. Okay. Now millijoules. So you can now in this chapter you easier to work with like those basic units. So the energy for the basic unit is joule, not a millijoule, not kilojoules. Right? Right? So first, you convert this into joules. Right? And for this one, very easy to convert is just replace this. So this M is milli, right? That equals, what is the numerical value for the milli? 10 to the what? -3. Okay. So 10 to the -3. Alright, so what you can do, you can just replace that little m by 10 to the -3. And then the other unit is simply the joule. And that's good, that's what you want. Right? Right, so X we still don't know. So therefore, we have to figure out this E photon, right? And now you tell me, how can we figure out that E photon? That E photon, which means the energy for one photon. We can either use that frequency or the wavelength, right? So two equations, and I will write the two equations somewhere here. And again, I will ask you which equation should we use. So we can either use E, so I will put a new notation here, which means for one photon, right? So E for one photon equals H times nu, or the other equation is E for one photon equals Hc, then what? Then divide by the lambda, right? Now, easier for this problem, which equation should we use? The second one, right? Right. So use the second one or use the top one. So that's our first step. But make sure you get the unit right, right? Alright. So what the number we have? I think on the test, I will give you the number for H. I will give you the number for C. You just know how to convert those units for the wavelength or the frequency. So 6.626 times 10 to the negative 34 joule times second. So this is the number for H. You agree? So what is the number for C? So I think most of you already also remember that is 8 times meter over second. Right. So now you can see this number on the top has a joule, have the second come out. Right? And you want to get this joule by itself, you have somehow count out this meter m, which means meter. Right? Right. So therefore, the lambda should be in what unit? Meter. Right? Right. So again, you can have one extra step, convert the nanometers into meters. So I will use this technique I used for the millijoules. Okay? So I will simply write 337, and I'll write something here. We'll see, like you convert that very easy. 337 nanometers. Just simply replace that n by the value. Okay? Remember what we did for the millijoules? So we said that 3.83 that liter mj. Okay? What we did, we replace that liter m by what? By the number it's standing for. What is the number for the liter m? It's 10 to the negative 3. So therefore we have that. Right? Now we do the same for that nn. Right? So what is the value for the liter n? 10 to the what? Negative 9. See here, when I just replace the liter n, by liter n by 10 to the negative 9. You still have the m. Now this m is not that liter m. This m is meter. Right? So therefore, I just simply just do something like this. So this is 10 to the negative 9 m. You agree? So these two guys together is our nn. Now let me erase those. So this guy, that is down to. Alright. So now let's see the calculation, and you will see that it makes sense. Really makes sense. What comes out first? Second comes out. What else comes out? Meter comes out. What do you have left over? Does that make sense? Yeah, because you want to get some energy. So it should be in joule or calories. So that's okay, right? Right. And do a calculation. So that is how much energy you have for how many photons? For how many photon? For one photon. So what do you get, Maggie?
5.89 times 10 to the negative 19.
10 to the negative 19. Is that right?
Yes.
17? Yeah. You just check you press somewhere, you press the wrong number. Do you get, for the age, do you use 10 to the negative 34?
Yeah.
Okay, for the C, you use 10 to the 48. Check that. You probably missed out here. So if you use what I did here, probably 19. You probably change both of that. So you don't change this number at all. 337, 337. 337. Okay? What we did is simply replace that n by 10 to the negative 9. If you change that into like also like right? Any other questions? No, right now, right? Okay, so we have 589 times 10 to the negative 19 joules. This is typical, okay? So when you have those wavelengths, so give you some idea, those wavelengths is about in the vicinity of those visible light. Okay? So this, the visible light about 400. So this they were like those UV light, because the wavelengths they were like smaller and the energy they were higher. Okay? For those kind of energy near the visible light, and for one photon, it's about 10 to the negative 19 joules. Right? So if you get something like that, so it makes sense. And if you get like too much, that means something is wrong. Right? So what do we do next? So now we have this number, right? So let me write them together. So we have one photon's energy is this. Yeah. So this number is, you can replace this here, right? So this is for one photon, energy for one photon. Now you have a number, right? So you can divide this number out, and you get the x number. Understand? All right. So what we say is, so let me just erase those. I hope you. Okay. So we have x equals 3.83 times 10 to the negative 3 joules, right? Divided by what do you say, 5.87, right, Maggie?
89.
Oh, 89. See that? 10 to the negative 19. This is what you need. Those are joules, right? Understand? Okay. Now let me just draw something like this. So this is the energy of what? Very good. This is energy of one, okay, photon. Now this on the top is what? Energy of what? Yep. All energy of the entire pulse. Okay. So in that entire pulse, we know we have some number of photon in it, and maybe like 1 or 2. Right? So to find out the number, and we have some of those assumptions. We assume all the photons have the same energy. That is reasonable because they have the same wavelengths. Right? Right. So what do you get? That's simple, okay? Remember, in the calculator, just make sure if you don't want to do the algebra, okay, don't want to do the algebra by figure out what are the exponents, okay? You just put it in the calculator. When you put that in the calculator, okay, so these two in the parentheses. Because otherwise, you think what you do, you are just actually you are going to this will be multiplied by this. Really literally multiplied on the top. Okay, you already find the number?
6.50 times 10 to the
6.50, 6.50 times 10 to the positive 15. Understand? So that's quite a large number of photon in it, right? Well, so nowadays you people use like the tetra gig for your for a hard disk for your computer, right? So a gig is 10 to the positive 9, a tetra gig is 10 to the positive 12. So now you have like 100 tetra gig. So that amount of photons, I mean that amount of 100 tetra photons. Right, so that's right. You are able off. I got 6.49. You get 6.50. 10 to the positive 15 photons. So very similar problem. So even though this one we have one average unit, we call that per second. You don't have to worry about the per second. Per second is the same as, okay? So what a similarity, you have the total energy. So this 100 joules is your energy for the parts. For the parts. Let's see, what's your, so we have this number here, right? So that seems like cool. Let me see your calculation.
Well, I just said
Minus negative,
yeah, minus negative.
that means positive. So you have you are already, and if you do that, this is not like a 3.37, still have 3.37. Now what that's what I saw the pattern, but now I saw that deeper to the 70%.
Yeah, okay, thank you.
Alright, so I just find out what Michelle did to get that negative 17. I think your calculation is negative 17, which means you use that number, the wavelength twice. I mean, the wavelength is 337 nanometer. You check that 3.37 times 10 to the negative.
Yeah, I did a point.
Yeah, so you did.
This one C.
This one C. Let me see how you get a C. It's the same as what we did, right? So you have the total energy, which is 100 joule, right? And what energy do you find out for one photon? What energy do you find out for one photon for this one? You probably take on negative 19, 2 paradigms, right? 2 paradigms. You get a photon of 68, yeah? And which is 2.14 times 10. What do you get? C? C. What do you get, Joe? So you first set in the meters, that's perfect. So that's, and then here is our HC divided by lambda, so you get 100 for one photon. This is 100 for one photon, joule, right? Okay, now, what is the idea? We have that we think about that for every 1 second, right? For every 1 second, that produces how much joule, that light. So that gives you like 100 joule per second. Okay. So now we think about that one second is 1 pulse. Okay. So in that 1 pulse that comes from 1 second, we have 100 joules. Okay. So 100 joules equals x times the number you get. Well, what do we get? What do you get? How do you get C? This will do the same thing. That is very like the first step, right? You solve that energy for 1 photon by using HC divided by lambda. Very good. Make sure you convert this to this. You still very good. You keep that 425 nanometer, then just adding 10 to the negative 9, that are 10 nanometer in meters. Very good. So that's about something 10 to the negative 19 joules. And so this energy for 1 photon. So you divide the total energy by 1 photon energy, you get the number of photons. Very good. Oh, what is that? The energy prior. So you have converse. Let's see, that's pretty much like 215. 215. So here you will have 215. I think the point is not 21500, right? It means 21500 3 zeros. And that's divided by this. So that will be how much energy is required for like 1 electrons to get out to come out of the atom. Right? That is energy. Energy, you want to, for this problem, you want to find out the wavelength. So you first find out the energy. This is for 1 mole. Yeah, that's just some idea like this. Right now, not those electrons. So just you find out this number. You just take like 21500. Then divide by the number. That will tell you kind of like the energy for 1 photon. For 1 photon. You don't have to divide by starting from that, once you get the energy for 1 photon, you will use that equation I write at the bottom, right? That get the wavelength. But that wavelength you get will be in meters, and you get converted into nanometers. Any questions? Okay, let's see, you want to find out how much photon in this much energy, right? So we know like what we talk about, we have that, we think about that 1 second. See that the problem tell you like you have this 100 joule per second. So the light give you this much, at this rate, 100 joule per second. In the example, we talk about 1 pulse. Right? And in this problem, we think about 1 second. So for every 1 second, how much energy we produce? 100 joules. Right? Now this question asks you, in 1 second, how much photon you produce? Right? So you can think about the 1 second and 1 pulse. Right? So in that 1 pulse, you have 100 joules. Right? So now you want to figure out in 100 joules, how many photons? Right? So you have that 100 joule. That's kind of like our total energy in that pulse. Right? So you have the pulse, in that 1 pulse, you have, and then 1 pulse, you think about that is 1 second. Every 1 second, you feel pulse that will produce 100 joules. Now, because all the photon in this kind of light has the same wavelength, right? So therefore they have the same energy. Right? So then how much energy 1 photon has? So this you call that E photon, right? Now how much photon we have here in this molecule? That's the question, right? So we don't know that number, we call that x. And then, now, once you get this becomes easy, right? Because this, you have that equation, so you will see that E photon equals, right? There are two formulas, right? Equals H times mu. If you want, you can just find out what is the mu, and then just multiply by H. Right? Otherwise, you can put two together. Right? So just, because this actually not two equations, just one equation in different way. Right? And so just write H times C divided by lambda. Right? It's kind of like a, you have those few questions, kind of confusing, right? And then plus, you have to make sure the unit is right. Yeah, right. So do a practice and find out what is the E photon, right? Do you do the same as what I was talking, right? So you first need to find out, right? You first need to find out, use this equation, and what is the energy, what is the sort of E photon. Do that, you have the number, you have the H,
Oh, you can
right?
multiply it by mole. The standard mole.
Got it now?
Oh, wait,
It's a good time to practice. Yeah, that's okay. So this will be 10 to the negative 9, right? That's why you get 10 to the negative 10y, actually you get 10 to the negative 19, right? So if you change that 10 to the negative 3 into 10 to the negative 9, you'll see this will become, not like 10 to the negative 25, become 10 to the negative 19. Okay, that's Google says you can that, you will see that.
Usually that's 2.15 cents or
Second.
Yeah, that's really good.
It would be 10 to the
What do you do next? So this is what?
This is the photon.
This energy for one photon, right? So they call it E photon. So you can imagine, so there are some like, for example, eggs or apples, right? Right? So you think about it, for every egg there's how many grams? So this kind of energy for is like the gram for one egg, right? And now all the energy for all the photons adding together equals 100 joule, right? And this kind of unit also is joule, right? Now, what do we have that equation there? X times what? This number times x, right? Write that number out. That number is that has 10 to the negative 19. Right. I think that's the answer is C is right. Any questions? Right, for this program, all those questions about one photon for one electron, one photon for one electron. So this give you this number here. You first have to convert this number into a joule per atom. That will equals a joule per electron. And that will tell you a joule per photon.
So start with what, low sodium?
You think about this 1 mole of sodium, and 1 mole of sodium requires that amount of kilojoules. So what do? You are starting from like 215 kilojoule over 1 mole, right? Right. So think about using like these two equations. I think everyone knows these two equations. 1 kilojoule. Use my technique. Just replace whatever this K is standing for. The K is standing for what? 1,000. Okay? So you will have 1,000 joules. So this one will use. Which one use first? Doesn't matter. So let me erase those. This is just what I tell you. This process. Okay? So we use those formula like those. This formula here is about for 1 photon. So what is creating a photon? Well, depends on the frequency of the photon. Some of the photon is produced from the nuclear. So now when the photon is produced by electron, that means 1 electron, 1 activity. What is the activity of the electron we talk about? We are going to see in the next section. Is about those transitions and between energy states. So you can imagine every electron in the atom have some energy in it. And so that you can just what you can do, you can stimulate. For example, you can use electricity. Not those electricity like that. You can use electricity to make the electron go to some higher state than usual. Then you will fall back. So each of those jumping up and down requires some energy. Then our assumption is, under some assumptions, there are some linear and nonlinear problems. So under some assumptions, we'll see like when you have those energy from like a higher state, jumping back to a lower state, that only creates 1 photon. Right. Now this, then you also know those kind of process like to dislodge or to remove 1 electron from 1 atom, and the electron's energy has to match in that light energy. What is light energy? Light energy has those small packets. It's not matching like the total energy. If you read the chapters, it's matching that the frequency is right. Right. So that's what I'm talking about here. Right? To see if you want to figure out those joule per atom, joule per atom that will be same as joule per electron. And joule per electron will be same as joule per photon. So once you get a joule per photon, then you can use those formula to calculate the wavelength or the frequency. It's very, very important to figure out this equation represents the energy for 1 photon. Right? So we have to convert this unit here into something like this. Right? Here is a joule, here is one photon, just one photon sometimes you see called one, right? Now what we need to convert? We need to convert two things. We need to convert a kilojoule into what? Into joule, right? So we are going to start from this guy, right, and go to this guy, right? So here is the unit you want to go, and here is the unit you're starting from, right? So therefore you have to convert in two units. You have to convert the kilojoule into joules by using this. All right. What else you can use? That's really your friend. One more is what? So one more is our number 6.022 times 10 to the power 23. Right. So once you have these two equations and do a conversion, so you will get this number. Okay? That's really become confusing. This number, you have a name, and this is what? Called E photon, right? And that's the number you see that many times in the other program. Okay? That is very important because once you have that, you can find the wavelengths, you can find the frequencies. Right. So now let me see how you convert, what number you get. Convert these two like 15 kilojoule per mole into how much joule per photon. What do you get? How much joule per photon? Yeah, I'm telling you, those two numbers make a usual sense, 10 to the negative 19, right? Once you get that, you can use the equation again. Right? You find out. Okay, let's see here. Let's see, this is a curve, right? So here, I think that's formula here. So here the formula. Yes, the kilojoule, that's okay. Here, this more as the denominator. Now you can see, if you want to count out the more. What do you want to get?
Can we work the problem on the board?
Okay, and let's take some time. Just try to do what I tell you. Okay? Let me erase this. So you try to do two steps. Okay? Try to do two steps first. Okay?
Yes.
And let me erase some of those numbers.
Yes.
Okay. Try to erase these numbers, and so let me just try to write out this. And then there will be another fraction here. Okay. So think about these two fractions. One of that comes from this. The other one comes from this. Okay. So try to use these two equations. That's really like what you learned from chapter 1, chapter 2. Right? So I give you that number 215 kilojoule and over 1 mole. You want to cancel out the kilojoule, you want to cancel out the mole by using these two equations. Can you do that? Right? So you have these two equations, right? And this one has a kilojoule and a joule. So somehow you can put it here as a fraction, cancel out the kilojoule. And here you have the mole. Right? You can do some arrangement to put somewhere here as a fraction, cancel out the mole. Right? That number you get is this number. Right? So do that first. And what you said again? You get 8? Yeah, so obviously you get that number and you put it into this equation. You know what is the h you're going to use is 6 upon 626 10 to the negative 34. What is c you use, right? And what you get from denominator will be meter, not nanometers. And then last step is very just common sense, like 1 meter is 10 to the 49 nanometer, vice versa. So you can do the conversion, right? I think probably you're right. Let me check your calculation. That,
I just got the total energy and then
very good. So
to divide it out
3.57.
to get the.
Yeah, same way. So I even sometimes recommend them to remove this number. But this number you're gonna use many times. This 5.9878 10 to the negative 25 is the product H times C.
Oh.
You can multiply H times C many times.
How many do you always significant figures?
Well, keep usually they were like this 1 3, so you keep like
98.
yeah. Okay now. Okay now what is computing? That's right. That's right.
Yeah.
That's right.
And then, is this the?
That's right. That's right. So that's yeah.
Yeah.
Okay, let me see. Yeah, that's very let's see, why
When you first,
it's not 0.626, 3.26, and also the number, sure is something of 5 times payment. So I think 6.6, what's the age? I think it's 6.626, you hear?
Oh, okay, I do that all the time.
Yeah. That's why sometimes you have to do the practice, just every time you do those,
Yeah.
and you first get this number first. So this number is the circle that the equation right on top, the E like a photon. And let me see what you get. You should get something 10 to the negative 19. No, that's not right. So this, I think it's this number, you forget, so this number I said there, see, 10 to the, I saw you do the calculation like with,
It's a 10 to the
10 to the 23rd. Yeah. Very good.
23.
23, that's our number.
Yeah, I know. I did that, so.
That's,
I'm saying I got like 30.
that's good, but you still want to have those like exponents. So keep, keep all those exponents. So do it. Don't. That's why you. Yeah. That's what it is. So that's why.
Yeah. That's right. Okay. Alright.
So it's approximately 8.
Yeah, I need to clean it up.
Yeah, you need to clean up. You need to clean up and see like what is exactly what are the exponents and yes. Yeah, that's.
Alright. Thank you.
You're welcome. Get it now?
Just to check.
27, that's how you use the calculator. Let me see your number. Perfect. Oh. Then you forget this number. That number means divide by that. Use divide. You cannot what you divide. Divide and subtract the exponent. But here is take this number, divide. Divide by 10 to the positive 23. 10 to the positive 23. 10. See here? Minus 19. That means this is the E photon. You can just write this.
Dude, it's funny you say that.
You can do it twice. You can do it a different way. What I tell you is you take this number times 1000, divide by that number, along, no 10 to 23, you get that 35,000. Then, see here, instead multiply, 215 times 20, you can see 21,000.
Daniel's got some decent math.
Divide by this number, 3. Very good. Now here is a 35,000 point, right? You forget that number. I tell you like two ways. You can either put that number in parentheses. You can also do like a divide by that. You know every number at the bottom has divided into the top. You can either multiply them together and divide into the top. Or you can divide them one by one. So you have two numbers here at the bottom, separated by multiply. It's not really multiply in the top. It multiplies the number at the bottom.
So we can pull this up and put it 10 minus.
You can do that, that's why I said.
So jealous.
Negative.
Negative.
Yeah, you somehow get like this one.
Very basic.
Well, that behind this model, if you have that, you will get 200 something here. You will buy that, you get 35. No, so 3.5. Yeah, you will get 35.
Yeah, you get 35.
No, 3.5.
Like a big
So then you have to move that one.
Now you can move one more. Okay, 35 equals 3.
That's, I like that.
Yeah, that's why. Well, they can be. If you use a calculator.
I understand the divide.
Yeah, you can either do it like this all around when you have like a 3, something. And you can just see like that is 2.95 times 2, that's I think yeah, why move the number you have if you have the calculator? Yeah, it's just put the error.
It was good. I stole a whipped cream can from
That's
work.
awesome.
And I duct taped
Oh,
it.
any questions? Did you get it? Yeah? You get it?
So I had my whipped cream on the pad.
You get it? Okay. You get it on?
Yeah, I got it.
Okay. Okay, so you get the answer is A, right? Answer is A? You got it? What's the time now? So now I'm going to talk about something that's conservative. Okay? So we learned one special concept called light, right? But light is referring again to all those gamma ray, X-ray, radio waves, cell phone waves, and so now we talk about those wave. Those light has wave characteristic, but sometimes they behave as a wave. They also have the particle characteristic, so the Einstein called them photons, right? So keep that in mind, and so now we are going to talk about some of the concepts here. Is about the relation between those the spectrum and the wavelengths. Okay? So I think that we talked about that before, because this equation. This equation, so we know that the energy of one photon, so I write that image size for one photon, is connected or is related to either the frequency or the wavelength. So conservatively, from this equation, it's very easy to identify. H is a constant. Right? So therefore, as the frequency, which is this nu here, increases, that is a positive constant. Therefore, as this nu increases, you will get more energy. So the higher the frequency, the higher the energy for one photon. Right? If you think about it, use the second equation. So we also write there separately. You can write them together as this, right? And H is positive, C is positive, so therefore it's also positive. And this lambda is in the denominator, right? So you take some number, divide by the lambda, which is the wavelength, right? So therefore that tells you the energy for one photon. So even though I did not write that as what I write on the board, and you understand this is for energy for 1 photon, is inversely proportional to the lambda, which means if the wavelength, this number, getting larger or getting longer, you take a larger number, divide into some other number which is a constant, you get a small number, you get a small e. So there are some of those radiation that has a very high frequency, a very like smaller wavelength, like the gamma ray, X-ray, and even though they travel with the same speed as the radio wave or the microwave sometimes you forget to stop your microwave and you open the door. But the modern microwave never stop by themselves. You boom, open the microwave door. That was not very harmful because the microwave those frequencies not that bad. So those they travel with the same speed. Travel with the same speed. And they are not really harmful. It's not because they travel slower or faster. So all those microwave, gamma ray, X-ray, the UV light, same speed. So why is harmful? Why is not harmful relatively? Is because their frequency. We have this whole spectrum. And we have those, for example, in this whole spectrum, we make it in this kind of pattern. We start with some of those radio waves on top. You will see those are the frequency at the bottom are the wavelengths. And you can see the wavelengths for this end of the spectrum, radio waves, is about 10 to the positive 5 meters. It's a relatively large number, about 100 kilometers. And then gradually the number getting smaller and smaller. That means your wavelength getting smaller and smaller and become 10 to the negative 15. On the top, you have the frequency. You know the frequency wavelengths for those kind of light inversely proportional. If the wavelength at the bottom, from larger to small, what will happen to the frequency is opposite, from small to large. And then you can check pretty much 2 of those numbers multiplied together. The top number is the frequency, multiplied by the bottom number, which is the wavelength. If the frequency is given in hertz, which means 1 over second, if the wavelength given to you in meters, right? So frequency times meter give you c, speed of light, and the speed of light is 3 times 10 to the positive 8 meters per second. You check that pretty much true, right? 10 to the 4, 10 to the somewhere between 5 and 3 here, 10 to the 4, and 10 to the positive 8. Because you multiply, right? You multiply 10 to the positive 4 with 10 to the positive 4, you get what? 10 to the positive 8. And then similar here, right? Yeah, similar here. 10 to the, this line, if you measure them, here is 10 to the 24. Now here it will be a little lower, maybe 10 to the 23. And here the 10 to the negative 15. Now obviously positive 23 minus 15 is about 10 to the positive 8. Right? So this gives us those kind of relations between the frequency wavelengths for different, this sort of the whole spectrum. Right? You probably have to memorize that. So it's very kind of like a very silly, stupid type of question on the quiz. I'll ask you like which form of radiation has a longer wavelength, right? If I tell you compare like a radio wave with gamma ray, and you remember this spectrum is very trivial, right? Compare radio wave with gamma ray. Radio wave have a longer wavelength, right? And you can also remember this one particular part. This is called the visible light. Visible light you have that red, and gradually go to violet. And the red has a longer wavelength, so this number here gives you a wavelength. And here violet has a smaller wavelength, right? So if red has a longer wavelength compared with violet, and wavelength and frequency are inversely proportional, and these two, no matter they are red or violet, and the frequency for the red and the wavelength for the red multiplied together so equals the frequency for the violet times the wavelength for the violet, right? So if red has a longer wavelength compared with violet, then whatever happens to the frequency, who will have a higher frequency? The red will have a higher frequency, or the violet have a higher frequency? Yeah, so therefore you will multiply a smaller wavelength times a larger frequency, and it will equals a longer wavelength times a lower frequency. Right, so those are very trivial. So I said this kind of a silly question. I give you this three forms of radiation: visible light, and X-ray, microwave. Right? And then ask you to put them in some order. Right? Now you will see this. Now you will see those order program in this chapter, next chapter quite often. Okay? Just know what do we mean by the increasing order or decreasing order. When I said increasing order, you're starting from something small, right? Or something lower, something less, right? Gradually getting more or higher. Understand? Right? So therefore, the first one you want to arrange in terms of wavelengths. Wavelengths called that lambda, right? And let's see the increasing order, right? Which means we want to find out the radiation that has the smallest wavelength. Do you remember which one has, on which side has a small wavelength? On the left side or on the right side? On the right side. On the right side you have the gamma ray, X-ray, right? Right, so we'll see X-ray will have the smallest wavelength. Right, so then in that way you will go from right to the left and find out those. So we'll use this symbol representing less than. So what will be the next? Next one with the visible light. Okay. So in other words, the visible light has a longer wavelength than X-ray. So that's increasing order, right? So the visible light has a longer wavelength than the X-ray. Then the last one with the microwaves, and that will have the longest wavelength. Right? So the second question about frequency. Frequency we call that nu. Right? And we know if you find out one pattern for like wavelength, and you just inverse it, because the frequency is inversely proportional to the wavelength, right? Right. So increasing order. Increasing order for the frequency. Now that will be starting from the one that has the lowest frequency. That will have the highest, the longest wavelength, which means what? Microwaves, which has a lower frequency than very good, than the visible, than less frequency than what? Than X-ray. X-ray will have the highest frequency in these three, but still like a frequency lower than the gamma ray. Okay? Right. So then C is energy per photon. Energy per photon. Remember we have the formula. We write that on the board. And we can see that E subscript photon equals. You can use either of those two equations. Okay? Probably use that H times nu because that is directly proportional, right? So if you have that, you already have that order, increasing order for the frequency in B, and then this one is same as B, right? So the order will be same as B. Right? So that's it about some of those conceptual problems. Alright, so you do a CRE, so for this CRE, I will give you this spectrum, so you probably have not remembered that yet. Okay? And this is only one part of the spectrum. Any idea? E? B. Very good, very good. So that's it. Yeah. Everyone understand? Now this one, be careful, is about every answer, every choice has different spectrum in it. Okay? Just examine one by one, make sure they are in the right order. Increasing frequency. Again, what? B. Okay. So this is also B, right? Yeah. B like bright. Right. So now, kind of we're going like back and forth. So we're going to talk about. We talk about those experimental results in the 1900s. Right? So those scientists find some of those experimental results that cannot explain by Newtonian theory model. One experimental result is about those atomic spectrum. Okay? So they take some of those spectrum from like one particular atom. We do the lab too. And so one particular lamp, the lamp we use pretty much emitting most of the frequency. But if you have a lamp, in the lamp there's only H2 gas, then your lamp will produce a kind of a reddish light, and not really like the usual light, like the sunlight. And you take those light with a prism, like a glass of like a triangle glass, right? And you separate those wavelengths. What you find out in the visible region, this is 4 line. So this is one result at the beginning of the 1900s. People try to explain. So why only these 4 lines in the visible region? So one scientist, it's a very good friend as Einstein. You see the 2 guys like Bohr and Einstein work together, go to the conference together, and so he's the one first proposed a model. It's kind of a semi-classical model, not really Newtonian model, not like the quantum model, right? So he quantized the energy. He said the electron in the atom is go around the nucleus like the Earth go around the sun. So those energy of the electron is quantized, and their like trajectory, their path is fixed. So that is the first model. Okay? So that model is very simple. Can explain the spectrum in the last slide. Okay? For the hydrogen atom, as for the hydrogen atom, and use Bohr's model, you can calculate. So what we did, you use those equations and calculate what are the wavelengths for that 4 line in the visible region. Use a very simple formula, and pretty much that formula will become an important formula for this traveler, even though that formula can be get from this model and also can get from the new model. So the idea is, as I already told you a little bit, is about those electrons has, like in that Bohr's model, has some of those fixed energy. Okay? And those fixed energy, according to Bohr, something like that, usually, so those energy depend on that number called the first principal quantum number n, and that number can have a value larger or equals than 1, 2, 3, 4, and so on. So that energy was fixed for like the electron in the atom. For the H atom, you can use that model, and that tells you something like this. Okay? When n equals 1, that has the lowest energy, that is very close to the nucleus. So that doesn't mean it's the only possible energy for the electron in the hydrogen atom. It can possibly go to some other energy, and we call them energy state or energy orbit. Right. So when the electron, go from those high energy states, for example, here, draw one picture here. We have this a relatively larger circle, has n equals to 5. Usually, the electron will not be there. One electron in the H atom will be here in this small circle. But if you use electricity or some of those stimulants, it will go up to some of those other larger orbitals. If somehow go to this 5, that's not stable. Usually that's will collapse, or fall back. When that fall back, it can fall back in different way. It can go back to 4, go back to 3, go back to 2. But one possibility is go from 5 directly to 2. So you can calculate, and if you go from 5 to 2, you will produce this violet line in the spectrum. Then we talk about those photons, like one photon from one activity of one electron in one atom. So you have one atom has, for some other atom has many electrons. But just think about in one atom, you have one electron doing some of those activity, going from 5 to 2, or maybe going from 3 to 2. So when that happens, it will create like one small packet of radiation. You call that is one photon. Right. And so those models in this chapter is about where are the electrons, what are the energy. So in the Bohr's model, we see the electron just go like around this nucleus like that. It's pretty much fixed as it's kind of very boring. The flat, so the electron always doing like that. Then obviously not possible because the atom is not flat. And so that is one problem. The other problem is use the result of that simple model. You can only predicting those lines for the H atom. We have some other atom like mercury atom and neon atom. If you have that equation, that formula will be totally wrong. Right. So then we have some other models, which means a new model, that quantum mechanics model. That works better, but still do not solve all the problems. Right? So how that new model come into existence? There's quite a few scientists work on that. Right? So they find out that spectrum, Bohr come out with that model, they find some other spectrum, Bohr's model doesn't work, and they measure some other behavior of electrons, and so they see that sometimes electron is really behave as an electron, like a physical particle, like like a small grain of sand, and so sometimes electrons behave as waves. So I will show you some of those experimental results as waves. Right? So out of those kind of experimental results, okay, and one scientist called de Broglie, okay, and he even proposed a formula to calculate what will be the wavelength for the electron wave. And he came up with this formula, which is lambda, which is the wavelength for the electron wave. How the electron can become a wave? The electron really smear out as a wave. Well, so sometimes you think about the electron's probability, the possibility is a wave. Okay? So electron is still a particle, the electron. So then you think about that wave of electron that has a wavelength that equals h divided by the m times velocity, which is the momentum. Right? So then you know what is h? H is the Planck constant, 6.626 something 10 to the negative 34 joule times second. Right? Then just be careful with the mass. Okay? You know that a joule come from a kilogram times meter square divided by second square. So therefore you have to use kilogram for mass. And velocity obviously will be the SI units. Velocity is distance divided by time. So therefore should be meter divided by time. So it's very simple like a formula. And simply write without all those units, without all those names, and the wavelength for the electron wave will show equals h divided by m divided by velocity. I think we can even do some calculation for those wavelengths of electron waves, compare with those wavelengths, for example, for those objects we see, maybe like the wavelength of a baseball. Right? And you see why the wave nature of electron is important. Right? So this example, you want to calculate the wavelength for electron. So what you use, the formula lambda equals h divided by m wave. Okay? Just remind you, h is our usual constant, 6.626 10 to the negative 34, right? And we initially use kilojoule times second. Now I'm going to replace the joule by kilogram times meter squared divided by second squared. Understand? So this is our joule. Right? So times second, so I'll still times second. Right? So divide by, you keep the units that will make a less mistake, right? So sometimes you forget to convert the unit, and you keep the unit, you will see they will not like make sense, right? All right. So mass is given to you 9.11 times 10 to the negative 31. Unit is what? Kilogram, right? Right. So you see if we use the right unit. And then the velocity or the speed is given to you also. So I think this question is relatively simple. Everything gives you in the right unit. And what you do, just know how to use the formula. Understand? Alright, and you can see this kilogram comes out. Right? So there's one s here, cancel out with s squared. Right? 1 meter here, cancel out with 1 meter squared. Right? Then you have a s left over here, you have a s left over there, so these two cancel out. The only unit left over is right now is what? Meter. That's very, very simple. Okay? So just remember, you want to use this number for h, and your mass should be kilogram. Okay? Your velocity or speed should be meter per second. Once you do that, and the unit will come out, you get how much meters. Okay? Anyone get some number? What do we get? So you get 2.74 times 10 to the negative 10 meters. Is that right? Right. So you can convert it into nanometers and so on. Right? Right. So you can take it like 2.74 times 10 to the negative 10 meter. Therefore, every 1 meter, you have 10 to the 49 nanometers. So therefore, you have a 0.274 nanometers. And that is a very, well, this wavelength is a very small wavelength, obviously, in terms of 10 to the positive negative 10 meters, very, very small wavelength, right? But you compare with the size of the atom. Okay? So it's comparable. So this kind of dimension, 10 to the negative 10, okay? It's about like the radius of atom. Okay? Which means those kind of wave of electrons that really can exist in the atom. Okay? And so therefore, you can really like measure those kind of behavior. You can use like those solid crystal or those like atomic crystal lattice, okay? And that will give you some of those the gap between atoms. Therefore, you can use as a grading system, and you will see those interference. But if you calculate what will be the wavelength for some of those objects, for this number, okay? And for baseball, and then you will see the wavelength for those kind of objects is so small compared with the size of those objects. And it's very difficult to find out a grading system to do the interference for the baseball. But you can still think about the baseball also have the matter wave. Okay? But it will not produce those kind of interference patterns because it's difficult to produce those kind of instruments. Have a small gap that's comparable. Because in order to get the interference, your gap, the distance between your two narrow openings should be very similar as the wavelength. If you have that wavelength, and your baseball is just pretty much bigger than all those, so you cannot see those kind of interference. You do calculations. So in this number, I give you those all the number ready. No, excuse me. This number is ready, but this number is convert, right? And so out of that, you are doing it very, very quick. I don't remember the number. What do you get?
C.
Oh, you see? Some get a C, some get an A. So obviously these two. Right. Let me see. What do we get? What do you use? We have the H, right? H is that. Yeah. Well, I put all those numbers because of the common. So this is the gram. They convert the kilogram. Convert gram to kilogram. Okay, so I think that is the one of those. What do you get? Let me see your calculation, let me see your work. Okay, 1 kilogram is how many grams? That's all. So use our usual way. Right? You write down 148.8 gram. You want to cancel out what? So gram. Therefore, what's the should be on the top? Huh? You want to cancel out the gram. Right now the gram is given you on the top, right?
Gram should be on the bottom.
Yeah, the gram from that 1 kilogram, you put 1,000 grams from at the bottom. So you go to the left how many times? 3 times. Right, so you get let's see, you first get this 148.8 gram, and you get 1,000 gram, 1 kilogram, right? See that? I see, right? I know like 3 hours, right? So you get 0.1488, and that's in kilogram, right? Right? So then now equals 6.626 negative 34. Then skip those, you get 0.1488, right? So this is kilogram, and then times 41.4. Check that with the numbers, huh? Okay.
Yeah, Greek chemistry.
Yeah. And then
What did it say?
for the fucking food one. What we're talking about is actually here. Where's the name? It was. Yeah. I'm just gonna go and tell him. 'Cause I was there for the food one. That was the.
You see, yeah.
I'm not gonna lie, I got fucking 0. It was 0.
Is that the right?
See?
Yes, see.
Yeah, we're for shit. Yeah.
Okay, now you see what is
It drops my grade.
So this is we talk about the behavior of the electrons. You see the electron behave. Okay, so the electron behave as waves. When the wave, how the wind is as a wave. So one common way to know something that behave as a wave is to say this is the parameter on the top. So if something behave as a wave, you can take a beam of something and use a omega. Then you try to detect what has at the back. If you see those bright, dark, bright patterns, this is the wave behavior. Because if electron not a wave, if electron really as to the sun, you only have 2 places to detect electron. There are 2 places divided behind. So this is the particle behavior. And that is the wave behavior. And people really find out about 1930 something. They use those. They use crystal. They have to use those. They use to get electrons. You cannot really create something like that with 2 openings in the order of electrons. So what they do, they use some of those, like those, for example, like the table salt, crystal. Then they will shine the electron onto that, and they will see different kind of patterns.
Can we try this slide again on Thursday?
Try the last one.
No.
What is interesting is also, if you try to detect the behavior of the electrons, so where do you see those kind of like those uncertain principles? So you try to measure, you see that pattern like this, then you try to wonder, if you have 1 electron, where the electron goes, where the electron like, come from this one or come from this one. You can measure that. You can measure that. Okay? You make the electron like just 1 at 1 time. Okay? You think about those patterns that come from many electrons put together. So then when they do together, they kind of like one electron come from here, the other electron come from here, then the interference. But actually, that's not true. Even if you have one electron come through square right now, one electron go from here, nothing over there, you still have to pattern. But if you detect that, you are lost that. You try to see, you don't try to figure out the electron going from left or right, you can do that, you can use a laser. But once you know that, you lost those kind of wind behavior. You're very aware at the beginning. Now what is confusing about the next slide I adding on that. Actually, that kind of makes sense, right? You don't know, maybe they are really his life, maybe they're bad, who cares, right? But I think that it's really don't make sense is it tell you like equally possible. It's equally possible. But if you think that if not because of those kind of uncertainty principles that come from that radiation particle, the radiation particle only have two possibilities: either emitting or not emitting. You know this model.
Didn't he like give up on this? Yes. And like thought it was worthless, and then like it ended up being super important?
Yes, is that?
But he had no idea. And then he went on to be like something stupid in physicist.
Like Einstein
Yeah, he like
and his
came
life.
up with this principle and it was like,
Yeah,
actually no, it's silly.
He tried to disprove that.
Yeah.
Right. So I think we were trying to finish this chapter.
I'm gonna get out of here real quick.